CLion, a cross-platform IDE for C and C++. Download now.
Hello, my name is Mathew Benson, and I'm very happy to be with you again at the C++ online conference. This time, I'll be speaking about command line C++ development. Right, a little bit about me. I'm a graduate computer scientist. I work as an independent C++ contractor. I really like C++. I also really like the command line. And I'm particularly passionate about energy efficient computing, like doing the most with as little power as possible. So here are my handles. Let's leave that up for a moment. Right, so this is how I thought to do this. I'll explain a little bit about my thinking. And this is kind of like an experiment, so I'm hoping for a little bit of feedback. It's an expression of some thoughts that I've been playing around with, things I've been researching on, especially with regards to teaching C++, like, bringing more people on board, helping those who are interested to kind of like not get lost, kind of like the way we have our volunteers right at the door of at the entrance of the, like the track rooms or the main lobby, helping anybody who is lost to find their way. Talk a bit about the command line. Just a few terms, clarify a few things that may not be so obvious. And we'll delve into playing with C++ on the command line. If we have some time, we'll also touch on some build system, some tooling that is particularly, shall I say, command line related. So this talk is actually, it's kind of like a continuation of last year's talk, which was C++ in the developing world, why I think it matters. And in that talk, I didn't mention some of the things I'll be demonstrating today, but it was, kind of like in a hand-wavy way. So today, my hope is to elaborate on that and, show a few more examples, play around, and, kind of like create a roadmap for anybody who is thinking of learning, like how do you get better? How do you start? How do you continue? How do you get better? And with particular emphasis on using the command line as opposed to IDEs as your learning environment. I don't have anything against IDEs, but we'll get more into my thinking as we go along. So the way I think about the command line, or as I've experienced it, there's a long history to what our computers look like today. You're likely on a desktop or a laptop, and if you look down at your keyboard, for those who may not have tinkered with the layout, you see the familiar QWERTY keyboard, the QWERTY layout, so to speak. And this layout has a long history, even beyond computers. Things like this, why are things shaped the way they're shaped? Why is the 9 where it is, or the Z or Z key where it is? There's a lot of history, and a lot of this gets lost along the way. And I think when you approach, especially languages like C++, or you're coming to computing in this day and age, the age of AI, where you kind of like, type a few words or request some assistant, and it spits out at you some words or some code or just whatever it is that you want. But I feel this takes away from something really core to our humanity. I feel like I'm fighting and advocating for natural intelligence as opposed to artificial intelligence. Not that AI doesn't have a purpose, but it must be subject to the natural intelligence. Because, I mean, you have to be confident. And, the work of verifying whether what AI has spit out at you is right or not right requires natural intelligence. And, in some cases, it actually ends up being double the work. So we need to build up the core skills within ourselves, within our users. Any person, using these technologies has to be in control. That even if something is helping you, you are the one who is in charge. So on the screen, there are these two gentlemen, and it may not be familiar to many, but this is Ken Thompson and Dennis Ritchie. One thing about this picture is how you see them working together. One of them is credited with the Unix system, and the other the C language. And this picture, I've been staring at it the whole day. So I've been preparing for this talk. And I really like how they work together. And I mean, if you know anything about Unix and C, it really works so well together. And C, as old as it is still a relevant language now. For those who follow the Linux kernel development, you may be aware that in the past few weeks there's been a lot of friction concerning Rust. Some people don't want anything to do with Rust, in the kernel, and there are those who are open to it. But if you think about it, it's taken a long time to get here, and C is still relevant. So is C++. So this is what I'm trying to do.
Why couldn't he, the cat, learn to play?
So I do hope that played okay. Put that in to stop myself from rambling and just get to the point. I want us to slow down and go down into the core things, and hopefully that will lead to a faster pathway to being better at C++ or helping others be better at C++. This is simply because our programming happens in text. Our compilers run with text. I mean, they're invoked with text. They spit out text. I mean, whatever errors, whatever they communicate with us, it's all about text. And as much as I appreciate what our integrated development environments try to do in trying to shield us from these mechanics, I think sometimes that can be more of a hindrance. It is something that I actually did struggle with earlier on when I was learning. And now that these days I, play around in the command line, I find that more concepts become clearer, easier, as opposed to, the wall of buttons that is, the IDEs. So I'm giving this proposal that learning should be done on the command line. It's not a rule, but it's my thought, and I hope you get to agree with me. So what we're doing is creating a playground. And this analogy that I gave in the previous talk about a child learning how to speak, that, as the child is growing in the first year, they sit there when they're not crying or sleeping or feeding. They're just watching you and listening to the parents, listening to those around them, and they play with what they hear. They play until they find the confidence to learn to speak. And if you really think about it, a playground is, it's like a safe environment where you get to express yourself and stretch your muscles and do what you may not be able to do, for example, in a serious environment, but through play, you get to build your confidence. And confidence is really the key here. So another reason for the command line, why I think it's very important, is it has to do with the cost. And this matters a lot when access to power is, like an issue, like you don't have stable electricity. It's something I run across here and there. And even sometimes when few experiments I've done is that if there's no power, if I'm away from an outlet, if I turn off all the GUIs and, get down to just have the command line on the laptop, it lasts a lot longer. It removes a certain battery and the battery anxiety. And I think with this skill, if you're more solid with the command line, I mean, the GUI is good. I use it when I can, when I have access to power. But it's good to have, like, I'll use an example of a raincoat, something that you can pick up when the need arises. The other reason is flexibility, especially with tools like SSH. I'm able to, connect to any computer anywhere and be productive, because I don't have to have a remote desktop environment to be productive. Even on a cloud server, when I'm up and about, I just grab my phone. I have a terminal up there, and I'm able to be productive anywhere, anytime, no matter what, because of the command line. And there are some things that you just can't do on the GUI. Some things are just faster and better done on the command line. So on to C++. C++ is a very important language, in my opinion, especially because of the access to system software and really critical code. If you look at the main APIs that are offered by our operating systems, they're either in C or in C++. And especially when performance matters, I did allude to the matter of low power use. When you need to cut out the middleman, there's a drive towards like the .NET based languages for the purpose of safety, but at what cost? Having that middleman may cost too much in some situations. So because of that, we need to build a knowledge of our languages so that we can also have more developers working on our bugs, getting rid of them. Just, basic literacy, the same way that, knowledge of languages helps us to communicate. So in order to do that, let's get started with the command line. Let's go through some very important terms in relation to the command line. And the first distinction that I would like to make is between the terminal and the shell. So start with the terminal. This is what the terminal looked like. It was a keyboard and a printer. And this evolved with the generation of screen technology, CRT technology, but the keyboard remains. Even now, keyboard, still the same, but our screens are OLEDs, LCDs, etc. So to the operating system, basically, a terminal is a combination of a printable surface and a keyboard, joined together in software. But in today's world, especially with the graphical environments, we don't connect to our computers using physical terminals, but we have programs that emulate these these older machines. So to get a terminal today, you open a program like Windows Terminal. I'm using something called Kitty. I also have Alacrity, Alacrity, and many others. So the next concept is a concept of a command line or a shell. Now, a shell doesn't have to be command line. A shell, if you think about it, it's like a protective surface for the system. It's how the outside meets the inside. So it's how our operating systems have been designed to receive communication and to communicate back. And text shells were the foundation, and they're still crucial even up until today. Though whatever graphical interface you use can also be likened to a shell. So there are certain programs that when you launch your terminal emulator, when you log on to your system, it launches. An example of this is Bash, Z shell, even the the CMD on Windows, and many others. But the main purpose is that they take the text that you type in and they run programs based on that. And they give you the output in text. So generally, there's a prompt telling you when to start. And the first word that you enter is generally the name of a program. If there's no such program, the operating system has a place where it searches. If there's no program, it tells you, I can't find, I don't understand what you just typed in, and wait for a prompt, wait for the next thing. So that's an overview of how the command line works. A few examples of shell types, based on the different types of system that we have. So for those who don't know, even Mac is based on Unix, like Linux. And Unix was a multi-user system. Because of the mainframe, you'd have people connecting to it on terminals, like many people connecting to one computer. But Windows has a different heritage. It has a heritage on the personal computer. So its systems were designed kind of like for one person on one computer. So it has a lot fewer commands, a lot less rich, but still as powerful, especially when it comes to development. I'd like to mention PowerShell, which is an attempt by Microsoft to, shall I say, revolutionize the shell and change it from being text-like to being object-based. And it's usually based on .NET, though you do type in text, but what you're manipulating is not so much programs, but .NET objects. But it's also compatible with the older system. So, the same behavior of typing in a program, the first word that you type in, it'll check for programs, but it also has this other capability on top of that. And as you get started with the command line, it can be quite daunting. When you turn on your terminal emulator and it launches a shell and you just see a blank screen, it's very intimidating. In fact, very many people are afraid of the command line because of this. There's no button, there's no, way to find out what do I do. But these systems had a way of asking for help. And the common convention, especially with, whatever program you're trying to run, is to put in the name of the program a space, and after that .h or -- help. See a typo there. But that each program, a well-designed program, will usually have instructions or a guideline that this is how I get to do my functionality. Now, the reason why I bring this up is because Unix and DOS are a bit different here, or rather the Unix-based and Windows-based are a bit different. For DOS, the convention for getting help is slash and a question mark after whatever program. And for PowerShell, because of the attempt to revolutionize the system, you type help followed by whatever .NET object, so to speak, is available for you. And it'll give you some text trying to show you how to use it. All in the with a pattern of program space, argument space, argument space, etc. So I've talked about text-based interfaces, but let me go over what text is just a little bit. For those who may not know, I know I'm talking to professionals here, but our computers are they work with ones and zeros. And we create, kind of like groups of these ones and zeros. And the smallest grouping that we have with our language, C++ and or C, is a byte, which is 8 bits. So each character is represented by a combination of 8 bits or more. Yes, I'll get there. So I'll start with ASCII. And what ASCII was a code using this number of bits, or certain number of bits, to represent characters. And this is an established standard, and it's something that has held true even up until today. So in actual sense, ASCII was actually a 7-bit value. And for those who do know, outside of ASCII, things went a bit crazy, because the attempt to fit all manner of characters into 8 bits, different approaches were taken, and many of them are not compatible, and it's a whole thing, which led to Unicode, which is what we use now. Unicode is standardization of text. And this involved adding more bits, to try and capture all of the characters possible from different languages, different regions. And it's been messy, to say the least. But ASCII, the foundation of ASCII still remains. And the encoding that is most commonly used now, but I'll say the foundation of the internet, is something called UTF-8, which kind of like pretends to be ASCII, but can do more. But I'll not go too much into that. But you could research on Unicode and ASCII. It's a wonderful, wonderful topic. In fact, there's actually a talk by James McNellis from cpponline 2014, 2015, somewhere around there. Excellent talk. Goes into great detail about this topic. So text and C++ and command line. The reason why this is important is because we write our programs in text. We speak text to we pass text files to our compilers, and they create programs which are not in text, but they're in machine language. So what is this machine language? So our processors, like over the years, they become much smaller, but what they are in essence is hardware programs. But we write programs in software and translate these hardware programs, or rather a language that is understood by the hardware program, which empowers our computers to work. So this distinction is important because, especially with C++, as opposed to other languages like JavaScript, our language, we have to write everything and compile it before we can run it. But there do exist other languages that kind of like are translated or converted to the machine language, but just bit by bit. But the problem with those is that those are really slow. So it's one of the advantages of C++. Right, so we'll get started with C++ on the command line. And we'll start with the compiler, which, as I mentioned, is a text-based program that reads plain text files with C++ in them and creates the compiled programs that can be understood by our hardware. So I earlier alluded to how to get help. And one of the first things is to know how to ask your compiler for help. With GCC or Clang, or Clang++, especially for C++, if you pass the option, the argument --help to it, you get a lot of text giving many options, but you don't have to know all of them for now. But it's just something that you need to be aware of, that it's something that you'll be doing a lot. How do I do this? Or how do I do that? On DOS, Microsoft, the compiler is called cl.exe. So pass the /? And that should give you like 3 pages of just many options many arguments that can be passed to the compiler. So let's get started with the first C++ program. I know many of you know what this is. Hello world. I'm going to do this using GCC. I know many of you can already see what's about to happen. But as I said, we're slowing things down in order to create a way of understanding, or way of learning, so to speak, a pathway of learning. So we get a compiler error. And if you look at the text that is given by a compiler, one of the things you notice is that, we see the top left, line 1, the name of the file. It says in function int main. If we go back to that, saying, okay, line 2 is int main. Talks about something not being recognized. And, it tries to be as verbose as possible. And even on line 5, it gives a suggestion. It says this thing called std cout is defined in header iostream. This is probably fixable by adding #include iostream. And it shows you even where to do it. And at the heart of it, this is how our IDEs work. They rely on the text interface of the compiler to help you to know what to do. So still trying to cut out the middleman. So here's the program with the suggested correction, and now compiles. And as a convention on our Unix-based systems, because we didn't tell the compiler what we wanted our program to be called, there's a default name that's usually a.out. With Windows, this is usually a bit different. And the name of the program is usually the name of the file, the CPP file, but with .exe at the end. So let's refactor our Hello World program and move the functionality, the main program, to a function called greet, and move it to another file called libgreet.cpp. The bottom there is the compile commands, one for the GCC, one for Windows. I'll kind of like ignore Clang for now, but I mean, it functions pretty much the same as GCC. Well, we get a different looking error. This time around, there's no mention of any file that we're familiar with, but it's mentioning something this called bind /bin/ld. So what this means in essence is that for programs to run, when we write a program that you expect to run, it needs to have a main function. It needs to have a function called main, and there are a few ways that can look, but it has to be called main, and there has to be a single one. So because the program we just created doesn't have a main function, it's not able to give us something that we can execute. So I'm going down this rabbit hole to illustrate the stages of compilation. This is actually illustrated even on the CPP reference site. There is a page that actually goes through the details, but I'm simplifying it a little bit. So there are 4 stages: pre-processing, assembling, compiling, and linking. I'll go a little bit into each of these. So until now, the first program that we did, we just passed the name of a text file that happens to have a program with a main function. I mean, our Hello World program, which everybody usually starts with. And the compiler assumes this to be an executable and tries to make an executable out of it. And because we had the main, it succeeded. However, with the libgreet, there's no main, but it doesn't mean that the program is wrong. And now we get into how to control the compiler with flags to, kind of like control the process. And we'll explore what that means. So the first stage is pre-processing. And what that basically means is there are some, in many C++ programs, anything that starts with a hash, there's look at the bottom of the screen there. There's the hash include iStream file. What this means is find this iStream file and include it with my current program. It just copies, it joins the 2 files together. So when we use the -e argument, we get to see what the preprocessor does. It's like, start the process, but stop after preprocessing. And this happens to spit out what it has produced on the command line, on the actual terminal itself, which if you give this a try, it really produces a lot of text. And this is what we feed to our compiler. So the next stage, after we have pre-processed that, we joined, kind of like assembled all of the bits and pieces that we need to convert into the machine language. The next stage is translating that whole wall of text, or that whole ball of text into, into machine code. But so we can stop that process, especially in GCC and Clang with the dash capital S. We can stop it at that point and get the output of what the assembly will look like. Now, assembly is a human readable form of the actual machine code. So this is what you get, on Compiler Explorer, for those who are familiar with it. This is what you get. This is what the website does for you. It stops, it just looks at whatever you've typed in on the left side, it spits out the assembly on the right, in essence. I haven't quite figured out a way to stop the process with MSVC, but it's possible to create a file that has this output. Just as an aside, this time round, it doesn't spit out the output onto the command line. It creates a file with a .s suffix. So the next stage is actual compilation, where there's all of the parsing, all of the processing, all of the magic inside the compiler to create what the system, the target system that you're targeting, understands. But to stop the process using the compiler, we use a -c flag or \c for MSVC. And the output of this stage is an object file, which by convention has the suffix .o. So this time around, the libgreet file that we created with the greet function, there is no complaint after you run these commands, meaning it was successful. It's also a convention on the command line. No output is good. Generally, output without provocation is not so good. So next and final stage is a link. And as the word suggests, we're joining something. We're joining object files to create an executable, perhaps. But there's also a way to link many object files into one. And this is how we get our libraries. And there are many libraries that store pockets of functionality, like our graphics library, DirectX, Vulkan. They consist of object files that have been compiled, and you get to use them in your program. Whatever program you're writing, this is how you get to interface with other people's work. And this is one of the superpowers of C++. The ability to combine efforts with other people by linking with what they have or what they've produced, so to speak. It's actually how we get to access other APIs on our own operating system, because not everything is exposed on the command line. A lot of functionality, very complicated functionality, is actually exposed through object files. So let's get back to refactoring the greeting program. So we've created a new main file, or rather a new translation unit. And here we have a main function, and we call the greet function that is in the library greet. So let's try and compile them together. Just as a note, we can compile more than one translation unit at a time. And the compiler is able to take all of this as input and put it all together, compile each on its own, create an object file, and smash them together and create the program that we need. But we still get a compiler error. And this is because the hello greet CPP file has no idea about the greet function. And this is because the translation unit, or the .cpp files, are translated independently. Yes, they may be linked together, but the translation process, compilation process, is one CPP file at a time. So enter header files. As you notice, sorry, we'll create a new file, call it library_greet.hpp. Note a different extension. We communicate with our compilers using extension, and they also communicate back to us using extension. That's why we have the .s suffix for assembly, output, .o for object files. So this is one of the ways that we get to communicate with our compiler, like what kind of file it is. So in this file, for those who don't know, remember we're going really slow. This is a function declaration. We're giving a name to a function, saying that there's a function called greet and nothing else. So when we include this file into the two executable units, the two translation units, sorry, library_greet.cpp and hello-world_greet.cpp, and compile, no output. Everything is fine. We get our a.out and get our greeting. So this is one part of how sharing works. Header files are very essential in communicating in text what is available in our library. And so to illustrate that, let's use a different library for communicating the output of our program. We'll create a new file called library_greet.fmt.cpp. Pretty much the same as the previous one. But this time around, instead of calling std_cout, we'll call something else called fmt_print hello world, hello format world. When we try to compile it as before, but this time with the new execution unit, we get a linker error. It tells us, I mean, I'll not go back into it. I'll not go so much into it because of time. But the point is, it's telling us it can't find this fmt_print function. And essentially, what that comes down to is we need to tell our program how to find the object file for FMT. And when we do that, I mean, it happens to be installed on my system. If you give me a minute, I seem to have a problem with my slides, but I could demonstrate it on the command line. Right, here we are. So we have our libgreet.fmt.cpp compiling, and it gives us the error. But with the -L flag, I just happen to know that, we're telling the system, look for a library called FMT on the system, and it's able to find our executable. And we're able to get to work with whatever library is available on the system. So I use FMT as an example, but the core thing I'm trying to illustrate here is that this is the superpower of C++. This is how we get to link, or we get to access pockets of brilliance that other people have come up with, and we get to share in the beauty of whatever systems we are accessing. So the core goal of all of this is showing how to play. How do you play with code. And say just have a few minutes, so I'll not go too much into it. I'm going to create a file called cmiclists.txt. And this is kind of like just a brief introduction to CMake, but tools like CMake help us to simplify the process I just alluded to. And in CMake, we get to play and to describe the process of linking, but in a simpler way. I'll go back to browser just a moment. I'll point you to the documentation for CMake. There's actually a very important page that if you go through it, it talks about how to get started with CMake. And CMake is important because it leads us into how to migrate onto more complex systems. You see, what I've just talked about is very, very simple. But we usually have to interface with much more complicated libraries, whatever programs we come up with. For example, our browsers and what have you, they link together so much functionality that you need tools that help you to communicate to the system what it is that you want to do. So, yes, the CMake build system. I'd recommend anybody who wants to get started with C++ to read this file. It talks about libraries and an overview. I mean, in a lot more detail than what I've just gone into. But the core reasoning I have, even as I conclude, is I've slowed things down to show you how to explore the systems that are there. Touring your compiler, getting to play around and see what is available, so to speak. Let's quit out of this. Getting to see what's available, getting to play around with programs. CMake is actually one of the programs, and it also has its help system. So get to know whatever tools you hear about and read about. Try to play with them. Just first things first, just go through the help file, just see, read the documentation. Especially especially compilers is an excellent resource on Linux for info GCC, which goes into lots and lots of detail about what our compilers can do. And I mean, it's a long journey. It's not something that can be covered in 1 hour. But my idea was to show how to slow things down and to play. So I think I'll leave it at that for now. Can possibly move on to questions.